Cool. So today I want to introduce single field slow roll inflation. It will be, well, there are many realizations of inflations. And I remember on the first lecture I told you, well, this is what I consider to be inflation. This is what I will call inflation. It's just a change of rules about how the universe expands and replaces the Big Bang. Yeah, that's the definition. So now I will introduce a model that achieves that. It's not the original model of inflation that was conceived, for example, by Alan Guth, who was one of the people that discovered or created inflation, whatever you want to call it. So in the first version of inflation, I will just say it in words. I will not describe it too many in details. This story is in the notes. It was basically a realization of inflation where inflation stayed inflating all the time and had to it had problems in escaping the state of inflation. Yeah, and it was possible, but it was troubling. So the universe had to escape via a phase transition. Yeah? But still, it was a convincing model nevertheless, so people insisted with it and improved on it. And then they created new types of inflation. So the one I will introduce is the one that is considered to be the model that works well, that improved on the problems that the first realization of inflation had, and by Alan Guth, and so this is called single field slow roll inflation. Yeah. It's typically attributed to Linde. André Linde is one of the people that conceived it. Also, Albert and Steinhardt. There were all other authors that wrote an early paper on this. Model, okay? Great, so that's what I will do today. Let me start with offering you the action. Remember, we will be writing actions now, from now on, and model the universe in a fundamental way, yeah? But remember, in the QA session yesterday, I want to insist on that, actions for me are just guidelines. You put on them all the symmetries that you want, yeah, and you put on them ingredients, and I will not take them too seriously. They just describe things that we consider the universe should have, the ingredients. Whether it's the correct action or the fundamental action, we don't know. And it's more likely that the fundamental description of the universe is not really achieved with actions. This is just an effective way to conceive the dynamics of the universe. Okay, so that's first thing first. So I will write it in the following way. Let me start by writing this one. So this term is gravity. I introduced there the Planck mass. The Planck mass, by the way, is 1/8 pi gn. Okay, so that's the Einstein-Hilbert term. So this contains everything which concerns gravity. You see the Ricci scalar. And then now I will add matter fields. And in this model of inflation, the only thing that there is in the universe at that time is a single scalar field. That's why the name over there, single field slow roll inflation. So let's write the simplest term into the action. Let's add a term into the action that describes the scalar field. And the simplest thing we can write is the following. Okay, it's that, okay? So in the previous two lectures, we've been discussing scalar fields, right? So this is not the first time I write this, yeah? And we quantized the scalar field with a quadratic potential, and then we discussed what goes on when we have nonlinearities. Yeah? But now everything is very different because we added gravity. So this will require some work. And the idea from now on is that we want to quantize this scalar field again, but we have this obstruction, which is gravity. We have and gravity, of course, describes the geometry of space-time, and so we will now be dealing with a curved space-time, and during inflation, space-time is super curved, yeah. And so those challenges need to be faced, and so we have 3 lectures to get to that point. So it will be there will be a lot of work in doing so. Yeah. Okay, if you compute the energy momentum tensor, which can be done in various ways, but the favorite way is, I mean, the simplest way is just to vary the action with respect to g mu only for the matter fields, and this will leave you to the following expression. Well, okay, so we have this. Okay, that's the expression for the energy momentum tensor. And now, in this part of the lecture, I will not consider yet fluctuations. I will concentrate myself only on the background geometry, right? On the background equations of motions. Yeah? So this will be the easy part of the discussion. So we will assume that in this case, that space-time has the very simple geometry described by this metric, no curvature. If you already dealt with exercises, you already know that inflation is very efficient at washing out the curvature. So after a few moments of inflation, we can just forget about K, the curvature. So this is all what is left after a little bit of inflation, right? So I am interested in the overall evolution of inflation, but I am assuming that after a while we can forget about K, so I will focus on that part of the evolution. Yeah. That being the case, you know that I think we have already discussed this in other lectures, right? With the energy momentum tensor can be parameterized as a perfect fluid under these conditions when the universe is isotropic and homogeneous, all of that. And if you then compare this with that, you just take it out, then the energy density for the case of a scalar field is found to be given by 1/2 phi dot square plus V of phi, and then the pressure is found to be this other combination. Those are the things that you will find out, okay? Good. Now, what is there to be? What is there left to be done? Is just to write down the equations of motions governing this system. And by the way, let me just insist that we have the scalar field, right? But we're just saying that this is only a function of time. It's just a background scalar field. So I will normally say background scalar field, or if I say scalar field, I'm just meaning something that only depends on time in this reference frame. Now, okay, the equations of motions will be, you have the Friedmann equation, which is given by, well, okay, I'll write them first in the more familiar way, which is with Gn, but you know how to convert Gn into the Planck mass. It's given by this. And then I just want to remind you what are the equations governing a flat universe. Those are the equations. And now let me write them for the scalar field that we're considering. Okay, so these are the very familiar equations that you know. And now, for the case of a scalar field, we have the following. And I will write them now. I will translate. I will put the Planck mass there because I want the Planck mass there to be present. I'll explain why in a moment. So this will take the form of, there you see the Planck mass now. 1/2 phi dot square plus v. And then the other one, this second equation, so obviously this is this one and this one. I will play a little bit with it, yeah, to simplify it a bit. And I will write the result, which is more convenient for the study of a system which has a single field in it. And it will look like this. Okay, so these are the two basic equations that we need to study the background evolution of inflation. Okay, that's it. Any questions? About nothing too sophisticated yet, yeah? So Friedman equation, then the second, these are the Einstein's equations, just written in an appropriate way for the study of inflation. Remember, the system is super simple. It has only a scalar field, nothing else, yeah? And the dynamics, what makes the dynamics interesting is the potential of the scalar field. If there were no potential, there's not too much to do, yeah? In the second equation, here there is the potential, but because I played a little bit, I used this one to make it a bit simpler. Then I obtained that equation over there. Okay, yeah.
Just in the context of inflation, we're using a cube that has x and t coordinates, right?
Yeah.
And it's an observable cube. What exactly does it represent physically?
Okay. For now, let me avoid the full answer because I will build up on the to get there. It is just some type of matter field. It's a scalar field. By now, we know that scalar fields exist in nature, if you want. So up until very recently, there was still the question whether they were fundamental or not. But now we know that the Higgs, there is a particle. So in this case, we're saying, well, let's assume or let's bet that at some time in the universe was dominated by a single fluid. The scalar field, there was nothing else. If there were anything else, it was so diluted that it didn't matter anyway. So we can describe the universe in these very simple terms. There is only one scalar field. Yeah, that's it. Yeah. So for us, this is a type of matter field. Yeah, and there is an associated particle, because if you quantize it, you can define some sort of particle state associated with it. Those are the quanta of the theory. But this is let's say, it's the condensate of that. Yeah, and I will go as far as there. Yeah, that's it. I mean, we can continue asking. Well, what's the real nature of this scalar field? Is it some known scalar field from some theory, from some interesting theory? Let's say string theory predicts scalar fields, or some other theory. For example, supersymmetry predicts the existence of scalar fields. Yeah. Fermions need scalar partners, and very often they are scalar fields, yeah, and so on and so forth. Yeah, so this could be one of those, but this is a general description. Yeah, it could be any scalar field. Maybe it is not justified that there is a single one. Maybe there should be two because there are two partners of a given fermion. I'm avoiding all of those details. This is just a first look into what goes on when the universe is dominated by such a thing. Yeah. Then we will refine things. I mean, how is it possible that the universe became dominated by a single scalar field and everything else is washed out? I'll go back to those questions. But for now, this is just a first look into what happens when the universe is dominated by a scalar field. Yeah. Any other questions? No? Okay, let's continue then. Okay. If you mix these two equations, you can play with them. For example, what could we do? We could take a derivative of this one, a time derivative, and then use this back and play with it. You can get to the following equation. It will not be a surprise that you get this. Okay, and what is this? It's just the equation of motion for the scalar field. So these were the Einstein's equations, but we can also vary the action against phi, right? So the Einstein equations are what you get when you vary the action against g mu, yeah? But if we vary the action against phi, we get this, which is, in the present context, is just a consequence of the Einstein equations. Why? Because you must remember that, that Einstein's, let's say, there is a restriction on Einstein's tensor, which is this one, which goes by hand with this one. So we basically did that to get this, yeah? That's all, yeah? Okay. And this equation is very useful. So one message here is that we have 3 equations, but only 2 are really useful. Yeah, you can choose if we can work, for example, with this and that. Yeah, or we can work with these 2. Yeah. So, but this is so familiar to us because it brings us back to just mechanics, single particle mechanics, because it looks like here you have acceleration. What would you call this? This is friction, right, produced by some damping term, and then just the force, yeah, the potential driving the system. Yeah, so this will be a conservative force pushing you towards some place, right? So this is very useful now to visualize what's going on. And let's say that here you have, you could basically solve this if you knew what is h, right? But we know what is h. Friction is given by the first equation, right? So we could say, well, friction, which is here, that damping term is just the square root of 1/3 m Planck squared, 1/2 phi dot squared plus v. So we have that. And this tells you then that, well, we know mechanics well, so we know what this equation is telling us. Yeah, we just need to draw the potential. If I draw you a potential, you know what's going on. Yeah? But this is very interesting because the friction term, the size of the friction, depends on this quantity. Yeah? But this quantity also has an interpretation in mechanics. Yeah? What is this? It's just the energy, right? Okay, so I'm making a mechanics interpretation of this equation. Yeah? So the amount of friction depends on the amount of energy that the system has, yeah? In terms of the scalar field. If the scalar field is the coordinate of some particle, following some particle. Okay, so now we'll draw you a picture. And this is the gist of inflation. And you will see this picture in every modern book of primordial cosmology. So let's draw some potential. It's up to you. You are, whenever you do primordial cosmology, you are allowed to create your own potential. Yeah? So now it's up to you what do you want to draw there. And I'm a very boring guy, so I will draw what I've seen 1,000 of times in different papers and books. So I will draw something that looks like that, okay? And we will imagine that there is, well, this continues to both sides, right? So this doesn't stop. So let's say our Lagrangian describes, has the fluid, scalar field fluid, that has this potential. The potential is part of the dynamics, yeah? And perhaps, because remember my attitude about Lagrangians, they're just effective descriptions. Perhaps this is valid only up to some point. We don't know what goes on if the value of the field is too negative in this side or too positive. We just know maybe you excite other degrees of freedom. So this is just a picture valid for a given region of this scalar field. Yeah? And for now, I will not really, I'm not interested in giving a quantitative analysis of this, for example, this height. This will not be important. So I will very loosely say, well, imagine that this height is large enough. Yeah? You have to ask, well, large enough compared to what? Well, forget about that for the moment. It's not a, and so what happened if you move from here to here, let's say? What happened to the potential in this picture? And It's very unfair, a very unfair question because I'm requesting to you to make a lot of assumptions about the scales and. Well, I'll give you the answer. Well, the potential doesn't vary too much. It stays almost constant. It's quite flat. Yeah. Okay. Now, if you go very fast from point to point, very, very fast. Again, this is an unfair statement because very fast compared to what? Yeah. Well, it might be that the kinetic energy is dominating. Yeah. And the potential has a very little role there if the movement is very fast. Yeah. Okay. So in that case, the potential doesn't matter too much, and the dynamics of a certain kind, and it's very complicated. Okay. Let us focus on the opposite regime. What happens if the velocity, the speed, is very small? Yeah, small compared to this term. Now I can be more specific. Yeah, so if the field is moving at a slow rate, yeah, then this guy will dominate. Yeah. Let's go back to the picture. So what I'm saying is that if the field is moving slowly, yeah, I'm referring to this part of the story, then what dominates, the kinetic energy is small compared to V, and that means that V is not changing too much. And what happened then? Then the damping term becomes dominant, yeah? So H doesn't change too much, yeah? Doesn't care on the value of phi, yeah? So remember, we can, basically I'm saying we can neglect this guy, yeah? In this scenario where the field moves slowly, yeah? We can forget about this guy, and now H depends only on the potential, yeah, roughly, but the potential doesn't change too much, and therefore H is insensitive to the potential, yeah? And so basically we have here something that is almost constant, H, yeah? Okay? And now you see what's going on, yeah? If this is true, what do you think it happens to the movement of this particle subject to a lot of friction? What do you learn in mechanics when you deal with such a system? So imagine you're here. Well, the potential still drives the dynamics because there is a force. Yeah, so the force is driving you to the minimum of the potential. You want to minimize the potential because the force is always the negative of the slope of the potential. But the thing you can do is to neglect the acceleration, right? Because the friction is so large that the particle is well, it might be accelerating, but this is going to be accelerating at a very low rate compared to this term here. Yeah? No, that's the point. That's the point. So if this is true, we can. I'm first giving you sort of an idea. I will show that this is true. Yeah, but I just want to think that okay, you might push the particle at a high speed, but the friction term will quickly damp the particle, and it will slow down. Yeah, and that means the acceleration will be negligible. And now the particle is just driven by the force, but the acceleration has a very little role in this because this is so large. Yeah. So we can neglect now this guy, yeah? Okay? And so, notice this, we have now a regime, an approximated regime, yeah? Just trying to follow this notion with your experience with particles in a single dimension. The regime is described by the following two equations. Let me write them, given that we made approximations here. One equation will be then that 3h phi dot is approximately equal to minus dv d phi. That comes from neglecting the acceleration, because we're saying that the friction is dominating the movement of the particle. And the other equation will be just 3h squared. I'm grabbing this equation, yeah, or well, this one too, but I'm just squaring it back, yeah, equal to 1 over Planck mass squared times v. So this is also approximated. Okay, so this will be the two equations coming out from these assumptions. Yeah. So what were the assumptions? The assumption is that the field starts moving slowly. So if, for example, I could grab the field, just put it there, release it, it will start moving because of the potential. It has to move somewhere. The potential is driving the movement. But the friction is so large that it's not moving fast. It wants to stay there. Yeah? Friction is and so the acceleration will be very small compared to the friction term. Yes? Right. Fair enough. If you did that, that's fine, because you see that potential is very flat. That's true, right? I draw a potential which is almost has almost no derivative, right? So one could say, well, let's do that. If you do that, then you have this equation. This is very easy to solve. And you will get very quickly to a regime where the field is zero, is moving with zero velocity. Yeah? So it will, and then you see, no, but if that's true, then what's going on with the potential? You see the need of not neglecting this back. Yeah? That's it. I will show this in a moment in more rigorous ways. It's just I want to give you first an idea of what we're talking when we say single field inflation. So this is called the attractor regime of inflation. Yeah? Yeah. Yes. Yeah. Perfect. Perfect. Look, the idea behind is that, as I explained in the first lecture, inflation is basically is a requirement that the Hubble radius is almost constant. Remember that definition? So we need h to be ideally a constant. Well, not ideally, that's not really ideal, but almost constant, right? And notice that in this regime, this is indeed what's going on. Yeah? If the potential is dominating, h only depends on the potential, but the potential is not evolving too fast because the speed is also evolving slowly. Yeah? So you see there is a consistency between these two equations. And so in this model, when the field evolves slowly, the potential stays almost constant, and therefore you achieve what we want. And now the universe is exponentially expanding. That's the idea. Yeah. Remember, this is the simplest model possible, and so we're putting the least amount of possible of ingredients in this model. Okay, you're asking quite a deep question. How did we get here in the first place? Yeah. I think that's a proper question for a Q&A session where I'm not recorded. Okay. But I want to refer to that point. I mean, it's an important question. Why did the universe start from this state? For the purpose of these lectures, I don't care. I just assume that all of a sudden the universe finds itself in this state. Yeah. And what I want to show you later is that such a universe creates precisely the fluctuations that you need for structure formation that we see later. Yeah? How did the universe get here? That's an open question, first of all. It might be a fundamental thing. It might be an accidental thing. I don't know. Yeah? I have an opinion, but I will not say it not for the cameras. That's another, yeah. Thank you for pointing to that. That would have been actually simpler, yeah. Thanks. Good. Okay, now I'll be more precise in ways that will be very convenient for later on. We need to parameterize all these statements. Yeah? So the idea here was to give you a first impression of what does it mean to be in single-field slow inflation. It basically means these two things. These two equations, which go hand by hand. And they are very good approximations, actually. If you study numerically this type of systems, they quickly go to that attractor where the system is super well described by those two equations. So they work pretty well. Yeah. Now I'll be more quantitative in the sense of defining the right criteria that make you understand when do we get to that point. Yeah. Well, I mean, what has to be the shape of the potential? I mean, here I just draw you a potential. It doesn't mean anything. A drawing can be very deceiving. Yeah. So let's define. Here it goes. Our first slow roll parameter, epsilon. This is standard definition. Nobody will make a different definition of epsilon, yeah, in primordial cosmology. So there's only one epsilon, yeah, and this it is. Yeah. To read it, you might want to think of this as a rate. This is just a comment. Yeah. It's a good idea to think of this as a competition. Forget about the minus sign for now. Minus sign, I will come back to it later. You can think of this as being dH, well, okay, just put it like this, okay, over, I'm not using space efficiently, yeah, over this, yeah. What do, yes, tell me. No, this is just a crude approximation that we want to achieve h equal to constant. It will not be exactly constant. It will be h will be lowering down its value. H will be becoming smaller and smaller, but very gradually, and that makes the Hubble radius to grow. Actually, is that the question? It's about the Hubble radius. No. All the contrary. Look at this. The h dot is actually negative, yeah, and that means that h is becoming smaller and smaller, and therefore the Hubble radius. Yes, the Hubble radius, which is equal to 1 over h, is becoming larger and larger, but very steadily. Yeah. Did that answer the question? Okay. Yeah. The epsilon is well, yes, you can think of, if you write it in terms of the Hubble radius, you will get something that I encourage you to see what it is. In this subject, we are more used to think about h than the Hubble radius because h is more, you can compare it with energy scales, you see, and so, yeah, so I will probably not talking too much about the Hubble radius itself, just about h. Yeah. So look at this. Epsilon is defined as a ratio between two rates. Yeah. One rate is the variation of h itself. There you have. So in the numerator you have how fast is h changing, and I'm comparing that with another rate, which is how fast is the universe expanding. Yeah. So epsilon means that it's a comparison between how fast is the Hubble radius, if you want, or the Hubble scale changing, compared to the how fast is the volume of space changing, if you want. Yeah, take it like that. Okay. So what do we want? We want a large epsilon or a small epsilon? Small epsilon, right? Because we want that h to be almost constant, but we have to compare it against something. And now I can be more clear about. Small compared to what? Yeah. Well, now you can see we're requesting that the variation of h is small compared to the expansion of the rate at which the universe is expanding. Yeah. So we will ask epsilon to be a small parameter because we need this movement of phi to be slow, right? And this is basically all. If you want, we don't want this to change too fast, and therefore we need this to be changing slowly, so to be almost constant, and this is the right comparison. Yeah, this needs to be small compared to this one. Yeah, so when you say small or large, it is always relative to something, right? So this is the way to do it in this case. Now, let me define the second slow roll parameter. This is eta. And here you might find differences between different sources or textbooks or authors. Yeah? I will take the right definition, and you might see other definitions elsewhere. Now, this is becoming the more established now. I will bet if you read modern papers on the subject, it's very difficult that they don't work with this one. Sorry, got it wrong. That's it, yeah? Okay, and here again, you can see that this is, if you want to think of terms of, well, what I'm really comparing with what, yeah? Here we're comparing the rate of change of epsilon against, again, the rate of expansion of the universe. So if we request eta to be small, then epsilon is changing slowly, and if epsilon is small, h is changing slowly, and so on and so forth. Yeah? We can actually define a third. Well, we can define as many slow roll parameters as you want. I will stop here. And this is just psi, and same story. Yeah. So it measures the rate of something against another rate. Yeah. And so they all, if they're all small, then things are varying very slowly in this system. Yeah, that's what we want to achieve. You can define a sequence of, in some textbooks you will see, let's say, this definition, eta n plus 1 in terms of eta n, yeah? So you will see this type of definitions of slow roll parameters. And so you can define an infinite number of slow roll parameters. But I will not do this here, it's not really necessary. Okay, now comes an exercise. I will not do this, but it's a good exercise, so I encourage you to do it. You can show, and this is an exact result, by the way. You can reconvert these two equations, which are exact also, reconvert them, play with them, into equations which only have epsilon, eta, psi, that's it, yeah? Play that game, yeah? And this is what we will find. I haven't told you yet what is epsilon v. I will tell you in a moment. And then the second equation is a bit more. The second equation is a bit more lengthy and perhaps less transparent. But this is my fault. This is the way I wrote it at the beginning, and I'm just sticking to it. Okay. And now, okay, so the statement here is that this is basically the Friedman equation. This is the second equation that we wrote. Yeah. In disguise, they look very different now. They have epsilon, eta, psi. And you notice that I have two parameters that I haven't told you what they are. And I will tell you immediately. So I will do it here. Okay. So epsilon v, which is, you find it very often also in these discussions, and eta v are defined in the following way. Well, I'll do it with a prime. Are defined like that. Okay. these are also called slow roll parameters, but look at them. They don't parameterize the rate of change of anything. Yeah? They parameterize the shape of the potential. Yeah? So if the potential is flat, well, no, let me say it in a different way. What do I mean when I say a potential is flat? Yeah? And what I mean precisely is that both of these parameters are small. That's the meaning. Yeah? So a flat potential is just my definition of flat potential is equivalent to epsilon v being very small, and also that the absolute value of eta v, which could be negative or positive, yeah, is also very small. Okay, that's that's what I mean by a flat potential. Okay. So now, all of this is exact, by the way. There's no approximation. Yeah. But now, please notice the following. If we have a flat potential, yeah, these two things are very small. That means, let's start here. That means that this is very small. Yeah. That means that this has to be very small. Yeah. How do we achieve a very small thing here? Well, either this guy is fine-tuned against this one. Yeah. But that's fine-tuning. The other option is that epsilon is very small. Yeah. Okay. But if epsilon is very small, then this is basically this over 3. Yeah, and this is multiplying eta times epsilon. So far, eta could be of order 1 here. Yeah? Okay, so eta is not required to be small. But then I do need this to be small, right? We know already that epsilon is small, yeah? And you just play with this, and you will realize, eta has to be small too. Yeah? Why? Because here we have, for example, eta multiplied by 3. Yeah? So eta times 3, yeah, equal to something which is small. Remember, epsilon is small, so eta has to be small too. Yeah? Okay, that's it. So a flat potential implies epsilon, the original epsilon that we defined there to be small, and eta to be small. And you can also infer that that's not all, but also psi has to be small. Yeah, there's no other way out. And that's it. Okay? So that's the proof of the first statement, that you can trust these equations here. Yeah? We needed to show it, really, we needed to make a more quantitative assessment and to be more precise about what do we mean by a flat potential. Yeah? So remember, a flat potential means this. And now that we achieve these two conditions, yeah, if the system starts in a place where this is true, then these equations tell you that, okay, the system, unless you fine-tune things, the system will be in an attractor movement, an attractor motion, where in the end this will happen. Yeah? And you know, if epsilon is very small, then h is almost constant. So now you have an exponentially expanding universe. That's it. Any questions? It is important that you actually work this out, yeah, because when you see it for the first time, you only see Greek letters, right? And it looks a bit confusing, yeah? But the message is very simple. The message is just that for a flat potential, this is a good approximation. Yeah? And notice also that if it is true that eta is small and stays small, then epsilon will stay small, and so on and so forth, right? So I mean, they're all tied together. Yeah. No, xi is just a statement that if xi is small, then eta will vary slowly. So imagine you're in a situation where, let's say you don't know the shape of the potential, yeah? because the potential could be whatever. Could be, for example, we could be here. Yeah. Yeah. So let's say that there is we have a mountain. The potential consists on this shape, and you're slightly here. Here, maybe you satisfy the conditions that are of flatness. Yeah. But then it might be if you move a little bit, just a little bit, and then flatness is completely broken. Yeah. And now you're not in the regime I want you to be. Yeah. So by having a small psi, you're saying that eta is changing time very slowly. So you move a little bit, and eta will continue to be small. Yeah. And given that eta is small and stays almost constant, then also epsilon will do the same, and so on and so forth. Yeah. So that's why one defines this sequence of slow parameters to ensure that you will stay for a long time in this regime. Yeah. So sometimes there are models where you can have epsilon and eta small, but just around the corner, the shape of the potential will make you to leave this stage. Yeah? So that's why I also ask psi to be small, and not only psi, but the next one, and the next one, and the next one, and so on and so forth, in order to ensure that this lasts for a long time. Yeah? That's the idea. Okay? Now, that's all I need. The rest is just writing papers with your favorite potential and asking questions whether will inflation last long enough, and the archive is full of that. So maybe you're too late in this business of coming up with your own potential, but if you do, here are the criteria. You have to play that game. Yeah? I actually want to escape that as fast as I can, because we are really interested in fluctuations. Yeah? So this is the background description. Now let's rush into the description of fluctuations. Yeah? So that's all I have to say about the background evolution of inflation. I won't say anything else. You now know that there are these slow roll parameters that need to be small. That's all you know. Yeah? They are time dependent, by the way. I mean, I'm not saying that they stay constant. They are time dependent. Yeah? And we will work mostly with this too. But you know now, they change very small, very slowly in time. Yeah? And these are the criteria. Okay? One last thing, because I cannot be so dismissive of this. What would you say? I mean, okay, we're staying in inflation for a long time. We start here. We're moving, always moving, always moving. The question tells you that you're always moving, but very slowly. Yeah. And then, when would you say inflation ends? Well, it's up to you. We need a criteria, and normally we say, well, this happens when epsilon is of order 1. Yeah? That's a rough criteria, because when epsilon is of order 1, you stop moving slow, and now you move quickly into the minimum of the potential. So as the story goes, is that this is just a visualization, right? Well, I mean, this little thing here on top of the potential means nothing. The state of the field is here, right? But this is just to show you that you're driven by the potential. You're moving very slowly, so you have inflation during all this time. Yeah? Very efficient inflation, but then epsilon becomes of order 1, and now you move fast, and now you precipitate to the bottom of the potential, and now the scalar fields start oscillating in the bottom, and this process gives rise to what is called reheating. Yeah? The details of reheating are often complicated. I will not say much about reheating. There are many things that will happen. Among them, oscillations, or maybe there were no oscillations. Those are details of different stages of reheating. But in a rough description, what happens is that the field starts to decay into other particles. And if this is very efficient, the universe gets thermalized very quickly. Yeah? And it gets full of radiation. This will happen in different stages. We don't know what are the first particles produced by inflation, but we know that the end process is a thermalized universe with the particles of the standard model. Yeah? That's a very complicated process, and very few people actually go into it. Yeah? So I encourage you to look into it and explore this kind of physics, which is fascinating. Yeah? Unfortunately, I won't say much more about that. And this is the real Big Bang, right? This is the explosion. Yeah, it's reheating. It's when the universe becomes hot. Yeah, so the universe was inflating before, and because inflation was happening so efficient, the universe is basically empty. Yeah? If there were any particles at the beginning, yeah, they got diluted, and there is less than one particle per Hubble volume, much less than one particle per Hubble volume. Yeah? So the universe is completely empty. Yeah? If you want zero temperature, up to the point of reheating where the universe becomes very hot almost instantly, in a very short time. Yeah? Right, right. Yeah, thanks. Yes, of course. If you start fast, you will very quickly slow down because of the friction. Yeah? So you can throw the field as fast as you want, but you won't get very far. It will get stopped by the friction. And now you get into the attractor region. It's as simple as that. Mm-hmm. Okay, next. Let's move on. Now I want to perturb this universe. This very simple universe. Inflation is amazingly simple. I have to stress that. Okay, we want to perturb the universe. So I will say things that have been said already, but very quickly, in order to get the minimal elements that we want. I will write again the metric, but this time I will consider perturbations, right? So this is not the first time you see this. The metric is just split into background plus perturbations. So these are metric perturbations. And you can start defining what is, for example, H naught naught. So I will use very standard notation. For example, you will find this in many textbooks. Okay, this is what you find in many textbooks. This has been spelled out already, isn't it? In a different form, or not? I don't remember. No? By the way, on this quantity here, this Dij is defined to be is that operator, okay? Okay, so what do you see in front of you? By the way, and we need to impose conditions. We need to impose that and finally, so I was forgetting an important character in this story, this guy, and this will respect, and then it has to be traceless. Okay, there you have. This part of the blackboard contains all we need to know about how to perturb the metric. Yeah. So let me very quickly remind you, the metric has how many components? It's a symmetric tensor. It's a 4x4 matrix, symmetric, therefore has 10 numbers. Yeah. All those 10 numbers are here in the form of perturbations. Yeah. They're all degrees of freedoms. Let me use that term loosely. So here you have one, it's a scalar field. Here you have another scalar field, yeah? Another scalar field and another scalar field. Okay. So we have 4 scalar fields, yeah? 4 degrees of freedoms. Then we have vector fields. Here you have one vector field. How many degrees of freedoms there are? How many? Okay, in principle 3 because it's a scalar field, but there is this divergenceless condition, right? So because of this condition, you really are dealing with 2 degrees of freedoms, yeah? Let me remind you very quickly that if you do a Fourier transform, yeah, of this field, you have that, but then if you ask this to be traceless, yeah, then you see what happens to the Fourier transform. This becomes just basically, well, with probably some I factor over there, you will have this condition. And given that this has to be 0, we have to demand that this is 0. Yeah? So that means that the fluctuation, the vector fluctuation is orthogonal to the mode vector. Yeah? And therefore, if you have the mode vector indicating in which direction there is this Fourier mode is propagating, then you know that the actual excitation, the amplitude of the mode has to live in this plane, which is orthogonal to the actual propagation mode, right? So there are only 2 possible directions in this plane, yeah, and therefore we have 2 degrees of freedom, not 3. Okay, so how many vectors we have? We have 1 vector, 2 vectors. So there you have 4 degrees of freedoms, 2 per vector, right? And finally, we have this component. This is called the tensor perturbation, yeah, the tensor mode. And it has this condition, but also has the traceless condition. So how many degrees of freedom do you think there are there hidden? 2. Why? Because we have 10 minus 4, so that's it was easy. But those conditions force it to be 2 in the end. And these are the fluctuations that Jose has been studying. Yeah. So Jose has repeated many times. We're dealing with 2 degrees of freedoms. Yeah. The gravitational wave modes. So these are gravitational waves. Yeah. We'll come back to them in the last lecture. Okay. And we can do the same for the energy momentum tensor. And I will just write them down. This is a very standard way of writing the fluctuations for the energy momentum tensor. You divide the energy momentum tensor into background plus fluctuations, yeah, and you need to decide how to parameterize them, yeah. And this is a conventional choice that I will write down. It's which is done about an expansion which considers that you are in a perfect fluid. Yeah. So this is, remember that when I wrote the tensor over here, the energy momentum tensor, where you have rho pi p, right? So this is sort of an expansion about that type of energy momentum tensor. An energy momentum tensor is describing a perfect fluid. So the first fluctuation can be written as delta rho, which is the fluctuation of the energy momentum energy density, minus rho h naught naught. So this, notice that we put by hand this term. Yeah, so you're free to do it. And then these are just definitions of how we parameterize the fluctuations of the energy momentum tensor. I will explain what is what in a moment. And there you have. This is the form that one can parameterize fluctuations of the energy momentum tensor. And I will add another term, which is pi ij. Does anybody recognize what is that? This? It's called the stress tensor. Yeah? it parameterizes deviations from a perfect fluid. Yeah? So if this is 0, you have a perfect fluid fluctuating. If we add this, now you're describing something more complicated than a perfect fluid. Okay, let me tell you, yeah, perhaps this is obvious, right? What is delta rho? Delta rho is just a fluctuation of the energy density. Delta P is also obvious, right? It's a fluctuation of the pressure, yeah? Less obvious is delta U. Delta U, to understand it, let me remember that I wrote this, yeah? This is one of the first things I wrote, but you can write it in a more covariant way. The covariant way to write this is, let me just remember it, is P G mu nu plus U mu, U nu, times P plus rho. Yeah, so this is a covariant way of writing precisely that. And here I introduce U, yeah? And U, mu, is just 1 plus 0 in this system. So this can be thought of as the velocity of the fluid, the forward velocity of the fluid, which is moving only in a long time, yeah? But if we are perturbing the universe, there might be fluids, part of the fluids that are moving slightly in a different directions, right? Because there is velocities, there are gradients of the fluids, yeah? So if we perturb the fluid, we're actually doing this. We're writing U as the background version, which is that one, yeah, plus deviation, yeah, delta U. And so these guys here are precisely doing that, yeah. You take the 3 part of the spatial part of this, which is just delta UI, yeah. You don't need the time part because this vector is requested to be normalized to -1 because it's a 4 vector, it's a 4 velocity, yeah, that this restriction exists. So if you know this, you know the time time component, yeah. And so you just need to make sense of this, and we often write this as the divergence of a scalar, which is just called delta U, plus delta U V, which is the vector part of the fluctuation. So you see this is a vector. We define a scalar part, which its gradient gives you the vector, but also we have a vector part. And the vector part needs to satisfy a condition. What do you think is that condition? It has to be divergentless, right? So this has 2 components too, yeah? So 2 plus 1, 3. Yeah, scalar, that's it. This is nothing too mysterious. We're just decomposing fluctuations into scalars, vectors, tensors, and that's it. There's no more to it. Cool. So, and we could do the same with this, but I will not waste time here because inflation is driven by a perfect fluid. So we can forget about the stress, okay? So in the end, the energy momentum tensor, let me just tell you, we will disregard this because it doesn't exist in inflation. So we only have this part over there. So how many fluctuations here? Well, 1, 2, and 3, 4, 5. We have 5 in the tensor part. Yeah. Well, no. It continues to be a perfect fluid. It's just that now it has fluctuations. I mean, you can always, locally, you can always reduce it to this form. You can always go back to that in a part of the universe, it will still have this form here. You can always do a change of coordinates that in that part of the universe, the energy momentum tensor leads you to this form. Yeah? So this is a perturbation which tells you how a perfect fluid changes from place to place, but by doing a Lorentz transformation, you can always get back to this form at that point in space. Do you see what I mean? So this is the perturbation of a perfect fluid, which remains to be perfect. Yeah, it's just it's perfect locally in every reference frame. Mm-hmm. Yeah, no, none of these will be hugely important because we're describing something which is so simple, a single scalar field, that in fact we are overdoing it. Yeah. But very likely you will find this expansion again next week when you study, for example, the CMB. Yeah? So you will encounter this again, and you will very likely see again this expansion, and you will very likely put back this stress component over there. Yeah? But this is not happening here. We are living in a very simple universe, and the inflaton which is a scalar field driving inflation, will no longer be exactly homogeneous. It has fluctuations. Yeah, we were studying now what happens when you are not exactly in a homogeneous anisotropic universe. Then it will have a component which is homogeneous, depends only on time. That's the background inflaton. But now we have fluctuations. I will call it just phi, var phi, right? So you have that. Yeah. Now, I wrote for you recently the energy momentum tensor for a scalar field, right? So take this, put it back into that expression for the energy momentum tensor for the scalar field, which was deleted a long time ago, and you will find the following. And compare it with this side of the blackboard. That's a great exercise. It's completely done in the lecture notes. And you will find that delta rho is equal to phi dot plus a derivative of the potential times phi. You will find that delta p is equal to phi dot minus v prime phi. And you will also find that delta u is equal to minus 1 over phi dot phi. Those are the things that you will find, and everything else is not there. So for example, you will not find a vector component for the velocity of the fluid, of the local velocity of the fluid. That's 0. Can you give any good reason why this is true? Who say that? Okay. I would say, well, it's connected to that. It's because we're dealing with a scalar field. It's a scalar degree field. So in the end, this is describing a pure vector. Yeah? So you will never be able to construct a pure vector out of a scalar field. Yeah? You can take the gradient of a scalar field to produce a vector, but we don't call those pure vectors. Pure vectors are constrained to satisfy the divergence. They are divergentless. Yeah? And so this guy, which is divergentless, cannot be produced by a scalar. But this is you see that this is there in the other side of the blackboard. So you have the fluid which is moving in different directions depending on which part of the universe you are, and they are following gradients of the scalar fluctuations. Yeah. So in which you're in a given point in the universe, you can ask, where is the fluid moving compared to the co-moving frame? Yeah. And a gradient of this scalar field will tell you, it's going in that direction. Yeah. With a minus sign, so it's going in the direction of the. So this is a potential for the fluid of the represented by the scalar field. Yeah. You're asking me about this guy again? Oh yes. Well, yeah. Yeah, precisely. This cannot be turned on by a scalar field. So this has all the conditions of being traceless, divergentless, so on and so forth. Yeah. So cannot be turned on by a scalar field. Mm-hmm. That's why I say we will not need it, and it parameterizes deviations from a perfect fluid. Mm-hmm. Okay, next thing. Where can I go. I need this, so I'll go here. We need gauge transformations. Again, I don't want to throw too many questions to you, so I will just remind you, yeah, that, yes, sorry. I couldn't get it. Yeah. Pi aj, yeah? Well, it just doesn't emerge and as a fluctuation. So if you put more ingredients, let's say the scalar field is not all there is during inflation. You can put more things. So I just wrote an action with a single scalar field, but you can put more things, for example, coupled to the inflaton. You could put something which is not a scalar coupled to the inflaton, and in that case, that could actually be turned on. So that term will be relevant for this discussion. But here, given that I'm considering only a single field, none of those things can be turned on. Yeah? So it depends on the ingredients that you decide to put in your model. Yeah? Studying, for example, what vector fields do during inflation has become quite fashionable recently because they're very interesting models. And so in that case, people pay attention into vector fluctuations and they study what happens with them. Yeah? But in this case, we have a single field, scalar field, so no vector modes, no pure vectors, only scalars. Yes. So in the end, sorry, for us, this is a good opportunity to tell you that if we are interested only in scalar fluctuations, we do not need to worry about gravitational waves, not for now. We don't need to worry about vector fluctuations, so we can just forget about them. And we only need to worry about these four scalar fluctuations. Yeah? You see four of them there, but there is only one inflaton. Yeah? So there is still an overabundance of degrees. Yeah? We need to figure out what's going on there. Yeah? Okay, so we will come back later to it. Yeah? But you all know, because thanks to Jose, you all know that the only true degree of freedom that gravity has is the tensor mode. Yeah? Gravity really propagates two tensor polarizations, right? So these are not real degrees of freedoms, yeah, the other four scalars. But what do we do with them? Yeah? Perfect. Yeah, yeah, it continues to be true. The only thing that stops being true is that if you go, for example, if you start considering non-linearities, then they couple together, right? So at linear level, you know that they propagate independently of one another, yeah? But if you add non-linearities, then they start to see each other, yeah? But nevertheless, the counting of the degrees of freedoms is non-perturbative, yeah? You will never produce something which is not there from the start. You cannot produce a vector field out of nothing, out of just scalars. Yeah? Yeah. Mm-hmm. Oh, I couldn't get the whole question. Okay, let's discuss it later. Yeah, yeah. Okay, so remember that we can always make a change of variables. Yeah, so if we are working with a given coordinate system, and you got bored of working with that coordinate system, you just move on to another one. So, well, let me say it in the opposite way. So you're working with X, you got bored with them, let's start working with X prime. But X prime represents a small change of coordinates. How small? Well, as small as this guy, psi mu. Yeah? Again, what do I really mean by small? Well, I'll be loose for the moment. Yeah? I won't be too precise. Yeah? And so, this is fleshed out in the notes. You can show that any fluctuation of any tensor. Yeah, let's talk about some tensor A mu nu, and you're studying the fluctuations of this tensor A mu nu. It could be anything. It could be the metric, could be the energy momentum tensor. It's up to you. Yeah. So, okay, you're working with some fluctuations with a given coordinate system. You got tired of working with them in that coordinate system. Now you move on to another coordinate system. So now you defined a new set of fluctuations. And because you're doing a change of coordinates, these have an effect on what you call fluctuations. So here I give you the recipe of what is the change on the fluctuations. And it so happens that it's not very, well, I would say it's fairly elegant. So your new fluctuations in the new coordinate system, yeah, will look like the old fluctuations plus corrections, which are produced by the change of coordinates. Yeah? And this will take the form where this is the background tensor, the background version of the tensor, plus lambda nu. That's the recipe. Yeah? This is the effect of a small change of coordinates on your fluctuations whenever you are studying fluctuations. This is valid not only in cosmology, it's in any context. Yeah? As long as you divide your theory between background and fluctuations, right? So this is the effect on the fluctuations. What else can I comment? Well, in the notes, I give a very detailed account on how does this emerge. And this is called, what's the name of this? This is called a gauge transformation. Yeah? And you all know that observables must be independent of the coordinate system, and therefore, given that this is just a change of coordinates, this has an effect on the observable, but if the observable depends on this, then we have to identify the right combination which is independent of this, right? So this is the way that a tensor looks, yeah, but we still have to identify what are the observables that we want. And we would like an observable that doesn't get modified by these transformations. So the theory has to be invariant under this set of transformations, yeah? And so now I can tell you what is the effect of this transformation on. My plan was to give you the effect on all the individuals, but given that I already argued why we are not caring about G and F, and I will focus only on A, B, C, and so on and so forth, so only on the scalars. And so you will learn that if you were working with A in a given coordinate system, or in a given gauge, you can stop working with that, and now you work with a new one, which is defined in terms of the old one, plus a correction. And this correction is just that. Yeah? Which A is that? Has nothing to do with this. We're talking about this A. Yeah? The pure time component of the metric fluctuation. Yeah? Let's now ask what's going on with B. You got bored with B. Now you want to work with B prime. And B prime is related to B through this modification. Yeah, I haven't told you what is, so psi mu, I hope it is clear that you can write it in terms of psi naught, yeah, the time component of psi, which is a vector. This is a vector, plus the 3 part, yeah? So you have now psi I. But again, psi I can divide it, I can split it into a gradient of a scalar plus a pure vector, right? So we can write this as a pure vector plus a gradient of something which we could call psi s for scalar, yeah, the gradient of scalar. This we will not need, so I can forget about that. And so we only have 2 scalar degrees of freedoms to modify, to make changes of coordinates, yeah? So we're very limited in possibilities of doing transformations here, yeah? Say again? I did, I think, no? It is over here. It is that one, yes. It's the trace, it's called the trace of the, yes. I'm not very consistent with my B's in general. Let's see what happens with C. It goes like this. That's the change that C experiences. And E, it goes like, I'm pretty sure you will see again all these equations next week. And that's how things change, okay? Now I can erase this, I think. Good, and what about, remember this, please, don't forget them. What happened to the energy momentum tensor after a change of coordinates, after a small change of coordinates? Well, the density fluctuation changes according to the following rule. Well, I'll just write the rule. The pressure changes as follows. And finally, the velocity potential changes according to that. Notice that they are unaffected by psi s. They're only affected by psi naught. Yeah. You can now play a game. This was a big development during the 80s. Yeah. At the early stages of inflation, people were trying to learn how to compute fluctuations and how to compute the power spectrum. Yeah, this is what we're doing. And people were doing it on different gauges. Yeah. And so they were sharing their results, and they were disagreeing, yeah, with one another. And there was a famous workshop in Cambridge where all the main people studying inflation gathered together, and they were competing with each other trying to compute the power spectrum. They knew that it was important. That was the one thing that had to be computed. And they were sharing the results, and they were disagreeing. Yeah. So nobody understood what was going on. But then Bardeen was there in the workshop, and he basically gave a good explanation of what was going on. Yeah? Well, the thing is that you're all working different gauges, and you need to work with gauge invariant fluctuations. Yeah? So the way out of this confusion is to identify, for example, of all these rules, you just pick up some of these rules, combine them together, and identify a variable which doesn't change with the gauge. And those are called gauge invariant fluctuations. And so you can play that game. You can just, I will not tell you all the possible combinations which are gauge invariant, but just pick up, for example, this one. I don't know, try to combine it with something else from here, and try to produce something which in combination doesn't change. Yeah? So these are called gauge invariant fluctuations, and I will just write one for you. There are many more, but I will write you the star of these lectures. Yeah? And this is called R, the gauge invariant co-moving Hilbert perturbation, which is defined as the following combination: is B minus 1/6 nabla squared acting on E minus H delta U. Okay? And that's the fluctuation Roman needs as an initial condition for studying. This is just an agreement, by the way. I mean, people doing primordial cosmology agreed with people which do late cosmology, let's say, let me just put a name for that. that we will give you this, yeah? And then you do whatever you want with that. So we agreed on the gauge. I will give you in the moving gauge, yeah? You will find papers doing many other things. There is, if you read the famous paper, we will comment on this by Maldacena, Juan Maldacena. He works with zeta, yeah? Which is another gauge invariant combination, but actually he really meant this. It was just a wrong use of symbols. So since then, since that mistake, it became fashionable to work with zeta, which is another. And when people work with zeta, they're most likely talking about R, not the real zeta, not the zeta that I will not write for you. Yeah. So let me just say this is okay. This is being recorded, but that zeta is the same in many papers. Yeah. Because it's a fashion, just to repeat the same mistake. It's done on purpose, okay? And almost nobody works with the real zeta now, which is another field that is a very respectable gauge invariant fluctuation, yeah? You can edit that out from the... okay, so last thing. Because I think I'm almost on time. Is that now I will choose the gauge, yeah? I mean, this is a gauge invariant variable, but it's still quite tough to go back to the action and work out what is the perturbed action for R as it is. Because now you have an action there. We wrote it at the beginning. So now you go back, you replace the metric, you put back the metric in the background plus fluctuation, and then you put a scalar field plus fluctuation, and you try to work out everything. It will be a mess. You won't get too far, yeah? So I don't advise trying that. So it is still quite recommendable to choose a gauge in such a way that in that gauge appears R isolated, yeah? So that gauge will be the following. We will choose the comoving gauge. You will see the reason of the name soon, where we will demand that, okay, you were working with delta U, yeah? You got bored of delta U, and now your new delta U, call it delta U prime, which is equal to the old one minus psi naught after the change of coordinates. You will demand that the new one is just 0. We will work with a coordinate system where there is no field velocity. We're just, so that's why it's called comoving. We're moving along the directions in which the fluid is also evolving. Yeah? So there's no velocity. We're choosing a coordinate system where we see the fluctuations of the fluid being always in the same spot. Yeah? This implies, so just take out the prime, by the way. This is just, you don't need to keep the prime. You can just say, well, our condition is just delta U equals 0 from the start. You see what I mean? We don't need to think too much about this. Yeah? So this is the gauge condition. Yeah? So I will do the same for the rest. We will demand that also E is equal to 0. And that's it. We cannot do much more, right? You agree with me? Because we had only 2 scalars to adjust, psi naught and psi s. Yeah? So we just adjusted psi naught here, and we adjusted psi s here. So that's it. We have nothing else to do. This is quite dramatic, by the way, because what does it mean to have delta U equals 0? Look around the blackboard and see if you spot what we're doing in this specific choice. Which side of the blackboard are you looking at? Should I get here? Yeah, we're demanding that the inflaton fluctuations are two enough. We're standing, just by choosing to move along with the fluid, at the same time, we're choosing a coordinate system where the inflaton doesn't fluctuate. It always looks like a background field. Such a thing looks strange, but it can be possible. There's no dilemma with that. Yeah? We're basically saying that we will demand that the inflaton fluctuations are 0. It's just a gauge choice. It has no deepness whatsoever. The fluctuations are still there. Yeah? Remember that this is just adjusting the coordinate system in such a way that you look at the universe in a different way. And now we're just writing, we're working in a frame where you don't see the fluctuations, yeah? The inflaton fluctuations. Nevertheless, that doesn't mean that the system is not fluctuating. I mean, they have been translated to another place. Remember, we were working with some non-vanishing fluid. They were there. We made a change of coordinate, and now we are in a coordinate system where they're not present. That means that we move the fluctuation from one place to another. Yeah? This is pretty much like what happens in gauge theories in general. When you can, by gauge transformation, you can move degrees of freedom from one place to another. In electrodynamics, for example, is the same idea. So by doing that, you have d is equal to 0, d is equal to 0, and now B is precisely R. Yeah? So now you can see that where R is in our perturbations of the metric. Yeah? So to sum up, there is no perturbations whatsoever in the energy momentum tensor, and there is only perturbations in the metric side of the theory. Yeah? That's what we just did. I think I will, time is up, right? Yeah. So this will be our starting point next in the next lecture. I killed, how many scalars I killed? I killed the inflaton, I killed E, those are 2. What else did I kill? Did I kill anything else? The inflaton, the E, and how many others we had left? Let's do the counting, because I'm worried now that I'm not... okay, C is still there. B is now is R, so B is our star, yeah? And who else is there? Is still A. So we have 2, we have our star, which is B, there is our star. Great, that's because it's R in this gauge, right? And we're interested in R, which is a gauge invariant fluctuation, it's the Q-moving corridor perturbation, yeah? But we still have these 2 messing around, and we cannot use the gauge transformation to get rid of them, yeah? So what's going on? What do you think is going on? Let me just play that. Let's try to anticipate what's going on there. What do you think is going on? Jose gave the answer, actually, yeah? Because you have been studying with him gauges and seeing what's going on with the... It so happened, we will start the following lecture announcing this result. When you look at how they appear in the action, you can prove, and this is true to all orders in perturbation theory, they have no time derivatives in the action. There's no time derivative whatsoever in these 2. What does it mean when you have an action and you have fields that have no time derivatives in them? They have a name. They're called Lagrange multipliers, basically. Yeah? So they lead to constraints. Yeah? So that's a good news, because they're not dynamical. They can be solved in terms of other things. So this is the true degree of freedom in this gauge. Yeah? So tomorrow, we will derive the action for B, yeah, for R in other words, and I will show you how to solve the constraints equations of A and C and write it in terms of R. Yeah? And we will have a very simple action which we will quantize, and we will produce the final result, which is the power spectrum of this quantum field. That's the purpose. Okay? Yeah, thank you very much.
Okay. Questions for Gonzalo? Yes, just a second.
Thank you for the lecture. Can you briefly introduce some reheating models? Can you introduce some like reheating models?
Reheating models?
Yeah, like what are the mainstream reheating models?
The main?
Mainstream.
Oh, okay. Well, it's not that there are models, of course. You need to make a lot of assumptions about how the inflaton is coupled to other stuff. Yeah?
Yeah.
Okay, let me say it in the following way. Let me draw you back this picture of the inflaton potential. So you have the inflaton goes down, and then it gets to the bottom, and then it starts oscillating. Yeah? By itself, the infladome will not do much, actually. We'll just start oscillating there, and it will take a long time oscillating. Not too much will happen. Yeah? Well, things will happen, but not interesting things. So you need to add to the action that I wrote at the beginning, how the infladome is coupled to other fields, to other particles, for example, fermions. Yeah?
Yeah.
And now you have to decide what are these fermions? Are they fermions from the standard models, or there's something else? Yeah. So those are the models, basically, in which you start constructing models of reheating, where you make assumptions about how the infladome is coupled to other particles, and ideally they're coupled to the standard model particles. Yeah. Because they, in such a way that when the infladome gets here to this point, it starts producing particles. Yeah. And it produces very relativistic particles because the infladome has a lot of energy to share with the system, so it starts decaying into fermions or other type of vector fields. For example, it could be coupled to the electromagnetic field, for example. So it starts producing a lot of radiation in form of photons and so on and so forth. Yeah. So that will be in a first approximation. What do you need to do to understand reheating? But then you discover this doesn't really work because of certain characteristics, so we better couple first the infladome with another field, yeah, which is an intermediate particle, which later on that field do decay into the standard model particle, for example, and so forth. So you can start making the model more complicated. So it is so model dependent, and we have so little information about what really went on in reheating that this is really black box yet. Yeah, we know very little about what really happened here, and we don't have too many ways to constrain what happened there. There's a lot of freedoms there to model this. Yeah.
Thank you. Like, what kind of mechanisms do we consider during this process? I know, like, there is parametric resonance and taconic effects. Like,
exactly.
Is there anything else?
Well, I'm not. Given that I'm not an expert, I'll probably, if I start listing all the possibilities, it will be very, very unfair about the type of effects, and yeah, I prefer not to, because honestly, there are too many ways to produce reheating, and I'm not an expert on the subject, so.
Thank you for the
So
answer.
I'll be very unfair if I start
Thanks for the lecture. I have a doubt about the choosing of common gauge instead of, for example, flat gauge.
Yeah.
Why do we choose common gauge?
No, it's just a choice. So here there is a decision of, let's compute the power spectrum for R and not anything else. It's just a choice of these lectures. We could have perfectly worked with a different gauge and, for example, compute the power spectrum for, well, directly the infladome. That's possible, yeah? Now, why, okay, that's one thing. But so you will find papers where they compute the power spectrum for the scalar field directly, yeah? Now, why are we choosing R, yeah? Which is just a choice? Well, R has nice properties, yeah? We will understand them tomorrow, yeah? R basically, if we examine the Fourier modes of R, we will discover tomorrow, that the Fourier modes, when the wavelength gets super stretched beyond the horizon, R becomes a constant, yeah? So it becomes frozen, yeah? And this is a property that you can show for R, that holds under very general conditions, and it's a non-perturbative, if you want, statement, yeah? So this famous paper by Weinberg, who study how does R behave, and what happened to R while reheating is happening, yeah? And so he showed that while reheating is going on, and there's a big mess going on in the universe, long wavelength amounts of R stays there. They don't find out what's going on at small scales, yeah? So R doesn't care about the details of reheating, yeah? So that's why we want R, because then it doesn't matter what happened in reheating. You have the initial conditions ready for other processes, for structure formation, for the CMB. Yeah. So it's an important choice in the sense that we want something that comes from inflation and survives all the mess that happens in small scales while inflation finishes, and perhaps many things happened in between inflation. There could be many stages of reheating, actually. Yeah, a first stage of reheating followed by a next one, and then a next one. We don't know. Yeah, coming back to your question, but then R doesn't care, and it still gives you initial conditions for the rest. Now that's half true because now we know how to mess up with R, and we know that we can add more stuff and that R. So, but this is at least in the vanilla model that I'm presenting, with this single field slower inflation. This will be true.
Thanks.
Sorry, I can't see how the H psi terms cancel in R.
You were computing the
positive one in B and a positive H psi in the last term as well.
Okay, nice. Maybe you are spotting a typo in my notes then. So you just grabbed E, I suppose, right? Is that correct? And put it together with B and yeah, is that correct?
Yeah.
And you verify that they don't cancel each other. Is that?
Well, it's the B and the H delta U.
Right, delta U. How does it? Well, delta U. The way that transform is here. Yeah. So you just grab this, put it there. Grab E prime, put it there. B prime, put it there, and you verify whether it continues to be B, E, and U, delta U, right?
Right.
Yeah. So if you made that computation and it's not, they're not canceling each other, it's because of some typo that I have. Okay. So I will need to verify, or you made a mistake in your computation. Well, let's check it out, please. Yeah.
Thank you.
No, but thanks for making that computation. So it's important.
Okay. One there. Here we go.
I didn't understand why, if delta U is 0, what happened to the perturbation of the scalar field?
Right, because delta U is proportional to the fluctuation phi, right? Var phi. So if this is 0, this has to be 0. That's it.
That means that we don't have the perturbation? Like?
Not in that coordinate system.
Okay.
Yeah, so we're adjusting the coordinate system in such a way that we shut down this. It is still there. I mean, the scalar field is a physical thing that is there, yeah? But we're just deciding to adjust our coordinates in such a way that we don't see it there. It moves to another place. It moves to B. Yeah. So now B contains, after making that change of coordinates, via Xi naught, yeah? So Xi naught, you just choose it to be equal to phi over phi naught, yeah? Yeah, and so it cancels that thing. Yeah, you can do it. And then now B has the
perturbation.
Exactly. Yes. Now B owns phi, yeah? Okay. It's funny we can do that, but it's just an artifact if you want. Yeah?
Okay. Thank you.
And what matters in the end is that we have this gauge invariant combination, which now maybe is not the correct combination, but we will verify it. Yeah.
Let's see, who had a question here? Yes.
Thank you, Professor, for your lecture. Just to clarify, I wanted to understand a little better the reheating process. What happens exactly at the minimum point of the potential? I see that like a stable equilibrium point of equilibrium of the potential. So you were speaking about what happens with the inflaton at that region of the potential. So what's the physical interpretation of that minimum at that scheme?
Yeah, I don't know. Yeah, the inflaton arrives here and gets eventually after, it could oscillate, but it could also just arrive in such a way that friction still is large, and then you get it gets slowed down to this point and just freezes there, yeah? Or it could take a long time to get to this point. It will depend on the characteristic of the potential here, yeah? So many different things could actually happen. But on top of that, the answer depends heavily on how the inflaton is coupled to other fields, yeah? And to what other fields are coupled. Are they coupled to a very massive fields or very light fields or massless fields whatsoever? And so really it's a very complicated process. And there are many options and many models of reheating that describe that, yeah? Okay, having said that, let me just give you some context. There was an intriguing question as whether the inflaton could be the Higgs. Yeah, look at that. How nice would that be? That the only scalar field that we know, which is the Higgs, which is actually a multiplet, consists of various scalar fields. One of them could have been the inflaton. Yeah, and that's quite minimalistic because we know how the Higgs is coupled to the standard model. So it could be that the Higgs, when it gets to the bottom, it starts to decay correctly into things, so it thermalizes the universe, and we know all the couplings whatsoever. Yeah, those models have a lot of difficulties precisely because we know so well how the Higgs is coupled to the rest of the standard model. So it doesn't work that well. But for actually very technical reasons, it's because the loop corrections that receive the Higgs when it's far away from the minimum are so large that they spoil the flatness of the potential and so on and so forth. So these are complicated models for that reason. Perhaps not because of the way that it decays on the standard model. But I'm not very sure whether people have really done the work, the full work of understanding how the Higgs will actually truly decay under these conditions for the Higgs potential we know, and so on and so forth. So it's a very complicated process. And trust me, I know very little people studying it in serious ways because it's messy. You have to compute loop corrections to it, and it's a complicated business.
Okay, so let's thank Gonzalo for this nice lecture. So now we go out, we freeze, and then we come back and reheat. At 2 p.m. there is a colloquium, okay? It's a colloquium of Jose